The 2020 Nobel Prize in Physics went in part to astrophysicists Andrea Ghez and Reinhard Genzel for their discovery of a supermassive compact object, a supermassive black hole, at the centre of the galaxy. But black holes are objects with so much mass that not even light can escape. In fact, the first image of this supermassive black hole, or at least its shadow, wasn't published until 2022 by the Event Horizon Telescope collaboration. So that begs the question, how did Andrea Ghez and Reinhard Genzel determine that this supermassive black hole was there? You can't see it. Well, it's true you can't see a black hole, and back in the 90s when they made these observations, you couldn't even see its shadow. You can see its effects. Before we go any further into the video, hello, my name is Thomas Rintoul. I've just finished my master's degree in astrophysics at the University of St Andrews in Scotland, and welcome to my channel where we dive into physics and particularly astronomy topics with minor diversions into studying these topics at university. If you're new, please consider subscribing and hitting the bell icon so you don't miss any future videos. Now let's get back to that black hole. You see, this supermassive black hole, known as Sagittarius A star, has a mass of around 4 million solar masses, 4 million times the mass of the sun. Something that massive is going to have a very, very strong gravitational pull, so strong that we can see its effects. Along with their teams at UCLA and the Max Planck Institute for Extraterrestrial Physics, Ghez and Genzel observed a group of stars in the centre of the galaxy moving very strangely indeed. When we think about stars, we tend to think of them as fairly static objects on the sky. They don't move from night to night, and our constellations remain unchanged when we can see them through the cloud cover. Honestly, why anyone chooses to do observational astronomy from Scotland is beyond me. I'm a theorist. In reality, stars are not static at all. Stars in our galaxy orbit around the galactic centre, the home of the Sagittarius A star black hole, and our galaxy itself moves through space, bringing all of us along for the ride. The universe is not static in any way. We can observe the movement of stars on the sky. You might have heard of the Gaia satellite operated by the European Space Agency. One of its missions is to track the movement of thousands and thousands of stars around our local bit of the universe. This motion is known as proper motion, and it's rather confusingly measured as an angular distance on the sky over time, the typical unit being arc seconds per year. An arc second is a unit used in astronomy because the angles we're interested in are incredibly small, much smaller than a degree. Because we have to deal with such small angles, we split our degree into 60 smaller chunks. We call these arc minutes. There are 60 arc minutes in a degree, just like there are 60 minutes in an hour. This still isn't small enough, so we split each arc minute into 60 arc seconds, just like there are 60 seconds in a minute of time. If we need to go smaller, which we often do, we then start using the sort of smaller units you might expect, like thousandths of an arc second being a milli-arc second. So we use these telescopes to watch how stars move, and most stars move a little on the sky year to year, typically in a fairly straight line. What was observed in the galactic centre looks more like planetary motion, with massive stars following elliptical orbits around some unseen, invisible central mass. What this tells us is that there is an object or objects in that central region of the galaxy with enough mass to completely dominate the motion of the stars around them, the same way that a star completely dominates the motion of planets. The conclusion from studying the motion of this cluster of stars, known as the S stars, is that this central body is a supermassive black hole. But while this is a really nice answer and a great discovery in its own right, this does raise a rather interesting question. How does this cluster of stars even exist? In most areas of the galaxy, stars form a fairly consistent distribution of masses, known as the initial mass function. This initial mass function looks something like this, with the peak of this typical IMF landing slightly smaller than the Sun. There are fewer and fewer stars as you go to masses much smaller than the Sun, and basically no stars once you get to several times the mass of the Sun. The probability decreases a lot. We classify stars by something called a spectral type, denoted by letters, and this spectral type roughly maps onto mass. So if we overlay these spectral types onto this plot, you can see that we expect that most stars will be K or M stars, much lower mass than the Sun. What we see in the galactic centre are a lot of O, B and A stars. the spectral types associated with the highest mass stars. In fact, the peak of the galactic center initial mass function is for B-type stars between 2 and 16 solar masses. That's really odd. Why is there this difference? One possible solution is that they formed in a cluster of stars that fell into the galactic center, and all the low-mass stars were eaten by the black hole, leaving this higher mass population behind. This is certainly what some astronomers suggested when the cluster was discovered. This suggestion has some issues, which were discussed in a paper by Gurkhan and collaborators back in 2005. You see, along with increasing the mass when you move spectral types from K and M up to O and B, we also see a decrease in the main sequence lifetime of these stars, the amount of time they spend fusing hydrogen into helium in their cores, before they evolve into red giant stars. By the time you're getting up to B-type stars, they have a maximum lifetime of about 1.5 billion years. Most B-type stars will have lifetimes much shorter than this. In fact, the most massive B-type stars fuse hydrogen into helium in their cores for only 10 million years. Unfortunately, this means that if this cluster was to have formed outside the galactic center and then fallen inwards, most, if not all of the stars that we observe in the galactic center at the minute would have already left the main sequence. They would have stopped fusing hydrogen into helium in their cores and potentially died in a massive supernova explosion. Check out my recent post on Instagram if you want to learn more about supernova explosions. Since migration of stars and stellar clusters is a process that depends on this fairly weak gravitational interaction to send objects moving inwards, there just isn't enough time for this to be a likely source of these stars. What this leaves is the scenario of in situ formation, the idea that these stars have formed where they are around the galactic center, around Sagittarius A star. Now, this poses a few problems for astronomers trying to explain this formation process, but before we can go near that topic, we need to have a look at what determines how a star forms in the first place. Stars, no matter how massive, form from giant clouds of molecular gas. These clouds of gas are mostly made up of hydrogen and helium, with some traces of heavier elements thrown in there too. Astronomers call these metals. Now, this cloud can hang around in space for a very long time until a very specific condition is met. This condition is known as the Jeans criterion, named for British astronomer Sir James Jeans. The Jeans criterion is a condition that must be met before a cloud or part of a cloud can collapse and start forming stars. This criterion is that the magnitude of the gravitational potential energy of the gas must be greater than the thermal energy of the gas. This means the pressure inwards due to gravity will be stronger than the pressure outwards due to kinetic energy, the temperature of the gas. Now, working through from some gas laws, we can work out the mass needed to collapse down to form stars. This is known as the Jeans mass, and it's dependent on the temperature and the density of the gas cloud. The exact mass isn't too important. As each cloud, or more accurately part of a cloud, collapses down, it's going to have a mass of around 100 to 1,000 or more solar masses. And as it collapses, it will fragment into loads of smaller sections, which then form your stars, which are on the order of 1, 2, 10, 20, or less than 1 solar mass, forming many, many stars that will make up this cluster. Several factors can affect star formation, to slow it down or to speed it up. Ultimately, if stars start forming, and the eventual masses of these stars is dependent on that balance of pressures, more pressure outward from hotter gas or gas clouds being pulled apart by some force is going to have an effect. Let's go back to the stars around our Sagittarius A star black hole. I mentioned earlier that most of them are B-type stars, yet in the rest of the galaxy, we'd expect far more K and M-type stars, lower mass stars. Something in that very busy, very extreme environment around that supermassive black hole is affecting how these stars form. Some are managing it, but some aren't. Something is opposing that collapse of gas to form stars. Something is giving us this very top-heavy initial mass function. That supermassive black hole is doing something. But that is a topic we don't have time for in this video, and we'll have to wait for its follow-up. Thank you very much for watching this video all the way to the end. If you found it interesting, then please do consider dropping a like and sharing it with a friend. If you're new, make sure you subscribe and hit the bell icon so you don't miss the follow-up to this video. The galactic center is a really interesting area of research, as is star formation. If you'd like to have a closer look at the small scale processes that allow stars to form, then why don't you have a look at this video about accretion, the process that allows stars to gain mass. If you like this video, I think you'll get a real kick out of it.